When we peer into the darkness of the night sky, seeing light that has traveled millions and even billions of years just to reach Earth, we are confronted with one of humanity's most enduring questions. How did the universe begin? For centuries, philosophers and scientists pondered the origins of everything, the stars, the planets, life itself. And only in the last century have we developed a scientific explanation that seeks to answer these profound mysteries. That explanation is known as the Big Bang Theory. The Big Bang Theory is the dominant cosmological model describing the early development and evolution of our universe. It suggests that the universe, as we know it, emerged from an extremely hot, dense state nearly 13.8 billion years ago. But how did scientists arrive at this conclusion? What evidence supports it? And what does it really tell us about the origin of everything we see around us? To answer these questions, we need to travel back to the early 20th century, when physicists were just beginning to grapple with the implications of Einstein's general theory of relativity. This revolutionary framework established that space and time were part of a single, malleable fabric, one that could expand, contract, or even warp in the presence of mass and energy. In 1927, Belgian priest and astronomer Georges Lemaitre proposed a radical idea. The universe was not static and eternal, as many then believed, but had been expanding from an initial primeval atom, a dense, hot state far in the past. To support his insight, Lemaitre drew on Albert Einstein's own equations, which suggested that the universe shouldn't be static. The fabric of space itself naturally expands or contracts, depending on its total energy content. Around the same time, American astronomer Edwin Hubble observed something extraordinary. By looking at distant galaxies, he noticed that their light appeared shifted toward longer, redder wavelengths, a phenomenon known as redshift. The more distant the galaxy, the greater its redshift. Hubble's groundbreaking discovery in 1929 provided strong evidence that galaxies everywhere are moving away from each other, indicating that the universe itself was expanding. If the universe is expanding today, it stands to reason that in the distant past, it must have been smaller and denser. Roll the cosmic clock backwards, and all matter and energy would have been squeezed into an unimaginably small, hot, and dense point, what we now call the initial singularity. From this singularity, about 13.8 billion years ago, the universe began to expand rapidly in all directions. This expansion wasn't an explosion from a single point into pre-existing space. It was the expansion of space itself, carrying matter and energy along with it. Every point in the universe was once contained within that tiny, hot, dense region. Now, the Big Bang Theory does not attempt to explain what caused the singularity or what came before it. Those are questions that remain at the limits of our current scientific understanding. Instead, it describes how the universe has evolved from those first moments onward. Immediately after the Big Bang, the universe was a roiling, opaque mixture of extremely high-energy particles. For the first fraction of a second, this primordial soup was dominated by fundamental forces and subatomic particles. In what's known as the inflationary epoch, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of all matter. As the universe cooled, the fundamental forces that govern physics today, gravity, electromagnetism, and the strong and weak nuclear forces, separated into distinct entities. Particle-antiparticle pairs formed and annihilated each other in rapid succession, leaving behind a tiny surplus of matter over antimatter. All of the matter that now forms galaxies, stars, planets, and life itself consists of this residue. Within minutes, the universe had cooled enough for protons and neutrons, the building blocks of atomic nuclei, to form. In a process called nucleosynthesis, these particles fused to create simple elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. The young universe was still a seething, opaque plasma, a fog of free electrons and nuclei scattering light so thoroughly that radiation could not travel very far. It wasn't until about 380,000 years after the Big Bang that temperatures dropped enough for electrons to combine with nuclei, forming neutral atoms in an event called recombination. At this point, the universe became transparent, allowing light to travel freely for the first time. The afterglow of this event, known as the cosmic microwave background radiation, permeates the universe even today. Detected accidentally by Arno Penzias and Robert Wilson in 1965, this faint, almost perfectly uniform glow is one of the most compelling lines of evidence supporting the Big Bang theory. The cosmic microwave background represents the oldest light we can observe, a snapshot of the universe when it was only 380,000 years old, providing a window into its infancy. After recombination, the universe plunged into simplicity, a vast, dark expanse filled with cold hydrogen and helium gas. This period, often called the Cosmic Dark Ages, persisted for hundreds of millions of years. But gravity was at work, drawing together clumps of gas, which grew and intensified until the first stars burst into existence. These early stars were colossal and short-lived, fusing hydrogen and helium into heavier elements and eventually exploding in supernovae, hurling these elements into space. Subsequent generations of stars and galaxies formed from this enriched material, culminating in the vast cosmic structures we observe today. So, what evidence supports this remarkable story? In addition to the cosmic microwave background and the observed expansion of the universe, another critical pillar is the relative abundance of light elements. The Big Bang theory predicts precise ratios of hydrogen, helium, and other light elements in the universe, and astronomical observations match these predictions closely. Furthermore, telescopes allow astronomers to look back in time, observing distant galaxies as they appeared billions of years ago. These observations reveal that galaxies and their structures evolve over time, consistent with an expanding universe that has changed dramatically since its birth. Yet, the Big Bang theory is not without mysteries and unanswered questions. For instance, what caused the universe to begin expanding in the first place? What exactly happened during those earliest fractions of a second, so brief and energetic that our current laws of physics cannot yet describe them with certainty? What is the nature of dark matter and dark energy, the invisible components that seem to dominate the universe's mass and influence its ultimate fate? To answer some of these questions, physicists propose extensions and refinements to the basic Big Bang model. One such idea is cosmic inflation, a theory that suggests the universe underwent an incredibly rapid expansion in its very earliest moments. Inflation helps explain why the universe appears so smooth and uniform on large scales, and why regions far apart in the sky look remarkably similar, even though they could not have communicated with each other in the conventional sense. Despite these complexities, the Big Bang theory remains our best scientific account of the universe's beginning, not only because it fits the observable facts, but because it continues to make successful predictions about phenomena astronomers find in the cosmos. It is important to understand, however, that the bang in the Big Bang was not really an explosion in the traditional sense. It was the sudden expansion of space itself, everywhere at once. There was no edge, no outside, and nothing to explode into. Space, time, and matter all began together. This is a concept that challenges our everyday intuition, shaped as it is by experiences in a three-dimensional, relatively placid world. When people ask, what came before the Big Bang? Or, what is the universe expanding into? The honest answer is that, within the context of current physics, these questions do not have definite answers. The beginning of time and space as we know it is, by definition, the point at which our familiar concepts break down. Some speculative models suggest a multiverse, countless other universes beyond our own, each with its own physical laws or histories, but these remain untested ideas at the edge of scientific investigation. At its core, the Big Bang theory paints a picture not of a cosmos that is static and unchanging, but one that has a history, a story that unfolds across billions of years. It tells us that the atoms in our bodies were forged in stars, born from processes set in motion at the dawn of time. The universe has grown, evolved, and, in many ways, become more complex, raising the possibility that it may continue to do so far into the future. As our understanding deepens, Driven by advances in telescopes, satellites, and particle accelerators, scientists continue to test and refine the Big Bang model. New discoveries only add to the sense of wonder, pushing the limits of what we know and highlighting how much remains to be learned. In summary, the Big Bang Theory provides a scientifically grounded narrative of the universe's origin and evolution, deeply supported by evidence and extraordinary in its implications. It is not just an answer to a cosmic question, but an invitation to probe deeper, to seek understanding, and to marvel at the astonishing journey from nothingness to the vast and intricate cosmos we see today.